The new section is entitled Bayes' Formula. Let us motivate this formula. First, let's state the name. Bayes' formula. Now, we know that set E can be broken up into two parts. You have E and you have F. You could be in E in this area, which is E intersect F, or, in union, you can be in E over here, not in F. You're in E, and you're not in F. That is, you're in E, and you're in F complement. And these two sets are clearly disjoint. They have nothing in common. So when I can take the probability of the left side, I get probability of E. And when I take the probability of the right side, since it's a union and there's nothing in common, I just can take the probability of each of those sets separately, this set and that set, and you can add them up. Now, keep in mind that the probability of E given F is equal to the probability of E and F divided by the probability of F. Now, the thing is, these three entries are real numbers. Just like 8 divided by 2 is 4, and you can say 2 times 4 equals 8, I can say P of F times P of E given F is equal to P of E intersect F. That is P, this numerator, P of E intersect F, is nothing more than this product. P of E given F times the probability of F. This is equal to P of E given F times the probability of F plus this. Now, the only real difference between that and P of E intersect F is now F complement. So I'm just really going to copy this down, and instead of F, I put F complement times the probability of F complement. If I call this set down here F complement, everything would work out. Okay. So that is what P of E equals. I'm in a position now to write down one version of Bayes' formula. The probability of F given E is equal to the probability of F intersect E, or probability of E intersect F, divided by the probability of E. Actually, okay, and this is equal to. Now, let us look at the probability of F intersect E for one moment. This is the same as the probability of E intersect F. But now, if you consider the probability of E given F, in Bayes' formula, we want to be able to interchange the locations, P of. We want to interchange the location of what's given and what we want the probability of. The probability of E given F is the probability of E and F, or F and E, divided by the probability of F. And we can always multiply those two. That is, this here, which is what I have on top, is nothing more than the probability of E given F times the probability of F. And the bottom, the probability of E, well, it's this mess in the bottom. It's the probability of E given F times the probability of F plus the probability of E given not F times the probability of not F. Now, it looks like a mess, but it isn't that bad. Okay, we're going to try real hard to be able to say in words how you do this, how you get this formula. Okay. The probability of F given E. For one reason or another, we don't know the probability of anything given E. But we know the probability of things given F. So, first thing, I interchange these two. The probability of E given F. Now, in the case before us, there's only two choices for things that are like F. Things are like F. Well, if it was a test, a true-false test, there will be two outcomes. True, false. False I'll denote by F, and true I'll denote by not false, F complement. So there's only two choices. So we always write down P of the first one. Given that, in the bottom, we put all the possible outcomes. It can be F, or always keep the first one the same, P of E. Or it can be not F. And for each of these probabilities, this one, and the one on top, we multiply by the probability of the given. In this case, P of F. Here, P of F. Here, P of F complement. And I doubt I made a mistake, but it's going to be exactly what I have here. Okay. Let us suppose there are three options. Maybe, let's see, what has three options? Okay, the size of closing. It's either small, medium, or large. So you want to know the probability that it's large given that you're a college student. It's the probability that you take size large given that you're a college student. But you're not given any information. You don't know. In the wording, you're not giving any information or probabilities that talk about, well, the probability of this given that you're a college student. You're only given conditional probabilities given the size of the closing. Okay? Well, that's the size of a closing. Bayes' formula says I can switch the probability of being a college student given that you wear large. Okay, in the bottom, we put all types of these. And they are small, medium, and large. If they were sodas, different flavor or sodas, well then I would put probability of closing and then the first type or soda. The probability given the second brand of soda. Plus the probability of closing given the next brand of soda. We don't have soda in this case. We have sizes. You can have large or you can have small. Spinning it down here. You can have medium. And always, for all the probabilities, multiply by P of this. Multiply by P of this. Multiply by P of, multiply by P of what's given. Okay, you're gonna have to be able to do that. Now, one of the things where I'm sure you're very, very confused is what type of problem would I come up against where I actually have to switch to given? We can't solve this problem given that you're a college student. But we know all of these probabilities given the sizes. What's the probability you're a college student given that you wear size L? We know that one. What's the probability you're a college student given that you wear size small? Well, we're given that information. We could have been given this information. For example, this is the probability that you're large and you're a college student divided by the probability you're a college student. Well, if you were given this, maybe it's a third, and maybe you're given this and it's an eighth, well, then you're done. Well, let's make that a 13th. Then you're done. The answer is 8 over 13, and you didn't need to use Bayes' formula. You use Bayes' formula when you don't know any probabilities, in particular the one they're asking, given this, whether it's college student or flavor of a soda or whatever. Okay, so let's see what's going on here. Suppose you're an insurance company. An insurance company declares a driver as accident prone. I will call that AP. Or you're not accident prone. I'll use the not symbol. Okay? Either you're accident prone or you're not accident prone. The company claims that the probability that an accident-prone driver has an accident in the next year is 30%. Okay, the probability that an accident-prone driver has an accident within a year is 30%. And the probability of a non-accident prone driver has an accident, well, this is going to be, of course, substantially less. Suppose 10%. Now, assume that a quarter or 25% of drivers are accident prone. 1 out of 4 drivers, the insurance company at least considers them accident prone. So here's the question. What is the probability that a new policyholder will have an accident in the next year? Will have an accident. Okay, so what we're asking is, what is the probability that you have an accident? Well, what is P of A equal to? Now, sometimes you don't actually use Bayes' formula, but it's still a problem in the section of Bayes' formula. Remember that A is equal to A and you're accident prone, or you have an accident and you're not accident prone. 100% of the people who have an accident, they either have an accident and they're declared accident prone, or they have an accident and they're not declared accident prone. Okay. Now, maybe I don't really agree with what I wrote here. What I said was the probability, well, let me say this correctly. The probability that an accident, an AP driver has an accident is 30%. The probability that an accident-prone driver has an accident is 30%. The probability that an accident-prone driver has an accident is 30%. So you are given that you are accident-prone. A for accident. The probability that you have an accident, given that you are accident-prone, is 30%. You are told that the probability that a non-accident-prone driver has an accident is 10%. Probability that a non-accident-prone driver has an accident is 10%. That is the probability. So you are given that you are not accident-prone. The probability that you have an accident, given that you're not accident-prone, is 10%. Okay, so P of A, reading this bottom line here, is equal to P of A and AP plus the probability that you have an accident and you are not accident-prone. Okay. Due to some constraint on my board, I need to erase that. Now, this here, this probability is the same as the probability of A given AP times the probability of AP plus this probability, I can write it as conditional, the probability of A given that you're not accident-prone times the probability that you're not accident-prone. But these probabilities at the bottom, I know all of them. The probability that you have an accident, given that you're accident-prone, 3%, 0.30, times the probability that you are accident-prone. Well, this line here. Assume that 25% of drivers are accident-prone. So the probability that you're accident-prone is 0.25, plus the probability that you have an accident, given that you're not accident-prone. That was given right here. It is 10%, 0.10, times the probability that you're not accident-prone. Well, if 25% of drivers are accident-prone, the remaining 75% are not. And if you multiply these numbers, ignore that 0. 3 times 25 is 75, but you have to go in 3 decimal places. You may ignore that 0 as well. 1 times 75 is 75, but you need to go in 1, 2, 3 decimal places. And if I'm not mistaken, you get 15%. In fact, I'm not mistaken. So 15% of the drivers will have an accident. Okay, the probability that a new policyholder will have an accident, probability of an accident, is 15%. There is no way to calculate the probability of having an accident. I was able to calculate the probability of having an accident given that I was accident prone. I was able to find the probability of having an accident given that I wasn't accident prone. But I couldn't directly find the probability of having an accident. Okay. So I'm going to do this, a very, very similar problem. So let me write down what we know. The probability of A given, the probability that you have an accident given that you're accident prone is 30%. The probability that you have an accident given that you are not accident prone is 10%. And the probability that you are accident prone is 25%. The probability that you are accident prone is 0.25. Okay. Now, the next question is, now suppose that a new policyholder does have an accident in the first year. What is the probability the driver is accident prone? A new policyholder does have an accident. What is the probability that he or she accident prone? Okay, so we want the probability of accident prone given that you had an accident. Now, if you look at the givens, you notice that what's given is about whether or not you're accident prone, not about whether or not you had an accident. If I reverse these two, what I'm given is whether or not I'm accident prone. In this case, accident prone. And in the bottom, I'm going to put all types of the given that. And there's only two. Either you're accident prone or you're not accident prone. And the probability of A doesn't change. Probability of A given that you are accident prone plus the probability of A given that you are not accident prone. For all of these probabilities, there are three of them on the board right now. For all three of them, you have to multiply by P of what's given. Accident prone. P of the given part. Accident prone. Times the probability of the given part. Not accident prone. And now we just write this up. The probability of having an accident, given that you're accident prone, the first one is 0.3 times the probability of being accident prone. The probability of being accident prone is 0.25. Now, it's always going to happen that what you have on the top is going to be one of the bottoms. And it happens to be the very first one. It's exactly the same. 0.3 times 0.25 plus the probability of having an accident given that you're not accident prone. Well, that's 10% times the probability of not being accident prone. Well, the probability of accident prone is 0.25, 25% of the population. Well, 0.75 are not accident prone. I would ignore that. If I removed the decimals in each term 3 places to the right, I will have 3 times 75. I moved the decimal 1 by the 3, 1 place to the right by the 3, and 2 places for the 25, Same thing in the bottom left. I moved the decimals 3 places, plus I move this 1 place, move that 2 places. I get 1 times 75. And the top is 75, and the bottom is 75 plus another 75. So I have 175 on top. I have 2 75s on the bottom. The 75s cancel. I have half the times if you are accident, you had an accident. I take that back. Half the times, and this is a pretty boring answer, but half the times if you had an accident, you were accident prone. And half the times if you had an accident, you weren't accident prone. Okay, because given that you had an accident, you're accident prone, or you declared accident, or you're not declared accident prone. Half the times if you have an accident, we discovered you're accident prone, and half the times you're not. It's a long way to show that maybe they shouldn't even waste time declaring people accident prone or not. Okay, so now you're going to take our test. You're going to take a multiple choice test. A multiple choice test. And the probability that you know the correct answer, and of course, if you do know the correct answer, you will put down the correct answer. I mean, in theory, you can know the correct answer, but for one reason or another, you might choose to fail this test and not put it down. And I am going to call this or denote this as P of K. K means you know the correct answer. And each question has 5 choices. So the probability that you guess correctly will be 1 out of 5. We'll call this P of G, the probability that you guess. Okay. And we want to know this. What is the probability? I want to make sure I ask this right. What is the probability that the student knew the answer, given that she got it right, she got it correct? What is the probability that you knew the answer given that it is correct. C for correct. Okay. Now, let's see what we know. The second line says that we know the probability that you know the answer is 1/2. The probability that you guess it correctly is 1/5. And on this test, if you know the answer, you put down the right answer. And if you don't know it, you guess. So what is the probability? Okay, so let us reverse this. Let us reverse this. Because I don't know this answer. I don't know, well, maybe I know one, but not both. What's the probability that you know it and you're correct? Well, if you know it and you're correct, you know it and you're correct. Well, this is just knowing it. Because if you know it, then you're correct. Okay, every time you know it, you're correct. So, if these are the ones you got correct, everything in this circle are the ones you got correct. So what's in this little circle is also correct. Because everything in the big circle is correct. These are the ones you knew. K is in C. The intersection is just K. The probability that you know it is 1/2. But the probability that you're correct, we don't know that. Because you can be correct in two different ways. By guessing or by knowing. We don't know this bottom one. We don't know the probability of being correct. So we try Bayes' formula. We switch it. We switch these two. The probability of correct giving that you know it. Now, this, what comes here, knowing? Well, there's two options. Either you know it or you guess it. So in the bottom, I'll put know, knowing it, and I'll put guessing. And for each of these probabilities, I multiply by P of that. I multiply by P of that. I multiply by P of that. Okay. Given that you know the answer, what's the probability you get it correct? 1. You're guaranteed to get it right. You know the answer. What's the probability that you do know it? 1/2. Probability that you know it is 1/2. On the bottom, what's the probability that, if given that you know it, what's the probability you get it correct? Well, that's the one we just did. It's 1. Probability that you know it is still 1/2. Plus, what's the probability, given that you guess it, what's the probability that you get it right? 1 out of 5. 1 out of 5 times. What's the probability that you guess? Well, if you know half of them, I take it you're going to guess on half. The probability that you guess has to be half. Now, since every one of these 3 terms all have 1/2, and some are in the top and some are in the bottom, you could cancel them out. So basically, you have 1 over 1 plus 1/5. 1 plus 1/5 is 6/5. And I'll keep the numerator the same, and I'll multiply by the denominator flipped over. 1 times 5/6 is 5/6. 5/6 of the time, if you're correct, you knew it. 5 out of 6 times that you got the correct answer, it's because you knew it. Okay, 5 out of 6 problems that you got correct was because you knew the right answer. And switching the conditional probability around enabled us to do such a problem. Okay. A classic problem for these Bayes theorem problems are medical problems. Taking a blood test. Now, when you take a blood test to find out if you have a disease or not, blood tests, or whatever type of test you take, they're not 100% accurate. You can have the disease, and the test will say you have the disease. That's a true positive. You could have the disease, but the test comes back saying you don't. That's a false negative. The test says you don't have it, you're negative for that disease, but it's wrong. Okay, you could not have the test, you cannot have the disease, and the test says you don't have the disease. That's a true result, and it's a negative. It's a true negative. You can also have a false negative. The test can come back saying you don't have the disease, but amazingly you do. All right. So we need to keep that in mind. Suppose you come to know that a blood test is 95% correct in detecting a disease when you have it. And detecting a disease when you actually have the disease. A true positive. You do have the disease. The test said you have the disease. The test says you have the disease. Only 95% when you do have it. In other words, if 100 people on average, in the long run, if 100 people came in who have the disease and they take this blood test, only 95 of the people will get a result back saying, yes, you have the disease. 5 people, the test will come back saying, you don't have it. But in fact, they had it. Suppose the test also has a say 1% false positive. False positive result. The test, say, gives a 1% false positive result. Does it give a positive result? Get a positive result, but it's not correct. That is, 100 people come in, they don't have the disease. That is fact. They don't have it. One of those people will take the test. Well, if all 100 took the test, one of them will come back positive. Yep, you have it, even though you don't. Okay, now suppose if 1/2 of a percent, 1/2 of, let's say 1%, 1/2 of 1% of the population have their disease. So studies show that 0.5%. 1 in 200 people have this disease. What is the probability a person has the disease given that the test result is positive? What is the probability that a person has the disease given that their test results, their blood test result is positive? D, I'm going to use the letter D for disease and P for positive, and in case I need it, N for negative. So we want to know the probability that somebody has the disease given that the test result is positive. Okay. Now, let us look and see what we are given. 95%, a blood test is 95% in detecting a disease when you actually have it. The probability of detecting the disease given that you have it. So the probability of getting a positive result given that you have the disease is 95% of the time. The test gives a 1% false positive result. What's the probability that the test is positive given that you don't have the disease? You came back positive, but since you don't have the disease, it's a false positive. This is 1%. And the probability of having the disease is not 1%, but half of that. 1% would be 0.010. But instead of, if I take half of 10, take half of 10 is 5. It's 0.005. Now, when I look at my conditional probabilities, the given that part talks about whether or not you have the disease. And the front part talks about the test result, positive, negative. Fair enough, we only have positives, but they talk about the test results. Over here, it's reversed. It's talking about whether or not you have the disease, given whether or not the test result was positive or negative. So, Bayes' theorem, I need to reverse this. Probability of P given D. D, you have the disease. Oh, there's two options. You can have the disease or not have it. So in the bottom, I put P of positive result, given that you have the disease, plus the probability of getting a positive result, given that you don't have the disease. For each of these conditional probabilities, multiply by P of that. Multiply by P of that. Multiply by P of that, the given that part. And these probabilities we actually know. The probability of getting a positive result, given that you have the disease, 0.95. Times the probability of having the disease, 0.005. This bottom one, bottom left one, is exactly the same as the top. You want to do it again? Fine. It's not a bad idea, but please at least check to see you got the same answer. It's a little bit of a check. Plus, the probability of getting a positive result, given that you don't have the disease, 0.01. False positive. probability of not having the disease? Well, if 0.005 have the disease, then subtract this number from 1. That is, do 1 minus 0.005, and you will get this number. And to be honest, I will leave you with the arithmetic. I would move this decimal 2 and this 3. Same, total of 5. Move this 2 and that's 3, total of 5. 2 and 3, total of 5. In other words, in my mind, there's no decimal. I would do 95 times 5. I would do 95 times 5. 95 times 5. In the bottom, I would do 95 times 5. 95 times good old 5. Over here, I would do 1 times 995. I would do 1 times 995. Even if you're using a calculator, do that. That way there's no errors that you didn't put the decimal in. There's no decimals in that problem. Multiply numerator and denominator by 10,000. And those decimals will disappear. Multiplying by 10,000 is just a command to move the decimal 5 places to the right. Okay, here's a fun problem. Suppose a detective is 60% sure that a certain suspect is guilty. A detective is 60% sure of a certain suspect. The detective is not 100% sure, but he thinks 60%. And in comes new evidence. A new piece of evidence shows that the suspect has the same characteristic as the person who did commit the crime. A new piece of evidence shows that the suspect has a certain characteristic in common with the criminal. With the criminal who committed this crime. The crime. There was a crime committed, somebody stole your bicycle, and the detective thinks that this person is 60% guilty who they picked up as a suspect, and a new piece of evidence, person has long hair, the person's bald, person wears pink polka dotted sneakers, some characteristic. The suspect and the criminal who committed the crime, they have this in common. Suppose 20% of the general population have this same characteristic. Okay, I spelled that wrong. Has the same characteristic. 1 in 5 people have this same characteristic. So the question is, How certain should the detective be now? The detective was 60% sure of the guilt of a certain suspect. But now new evidence came in, and you know what? It matches the suspect. The suspect has a bald head, just like the person who committed the bicycle theft. They're also bald-headed. So, that's going to up how the detective, the percentage that the detective feels you are guilty or this suspect is guilty. Okay, what probability should the detective now assign for guilt of the suspect? Remember, percentage and probability, they're the same. This 6 out of 10 or 3 out of 5. That's the probability. So, the probability that this person is guilty, given that you now add on this new characteristic. Okay. So, what is the given? What I just wrote down, this is what they're asking. What is the given? Well, the probability that you have the characteristic is 20%. That's this line. The probability of guilt, is 60% initially. All right, so we are going to switch these. The probability that you have this certain characteristic given that you're guilty. Now, the second part, the one that comes after the given, that is guilty. Well, there's only two options. You're guilty or you're not guilty. So in the bottom, notice the P or C doesn't change. This part never changes. It's that one that's going to have all the possibilities. You can be guilty or you could be guilty. And for each of these probabilities, we multiply by the probability of the given that, guilty. The probability of the given that, guilty. The probability of the given that, not guilty. Okay. Now, given that you are guilty, the probability that you have this characteristic, the probability that you are bald is 100%, because it is known that the guilty person, the person who stole the bicycle, has bald hair. Okay, given that you're guilty, the probability that you have this characteristic is 100%. The probability that you're guilty, 0.6 or 0.60. In the bottom, the first part, exactly the same as the top one. Plus, you're not guilty. The probability that you have the characteristic, 20%. Only one person is guilty. Of everyone else in the world, 20% of them have this characteristic. The probability that you are not guilty, well, the probability of guilty is 60%. The probability of not guilty is 1 minus 0.6. It's 0.40. 0.40. I would, in the first term on top, I'd move the decimal 2 places to the right, get 60. 1 times 60 is 60. In the first term on the bottom, I'm going to move the decimal 2 places. I choose to move it on the second number, making it 60. 1 times 60, 60. Plus, in the bottom. And move this decimal one in the second term. Move this decimal one place and this one place for a total of 2 places. 2.0 is 2. 4.0 is 4. 2 times 4 is 8. It's 60 out of 68. Divide the top number by 4, you get 15. Divide the bottom number by 4, you get 17. 15 out of 17 times, this person will be the correct guilty person who stole the bicycle. Number 6. I think there's 3 cards. I think this problem is the 3-card Monte game. Okay, it's this 3-card Monte game. You have 3 cards. The shapes are identical. Other than the writing on the cards, they all look exactly the same. One of them, the top is red, the front is red, and the back is red. And the second card, the front is black, and the back is black. On the third card, one side is red, the other side is black. The first card, both sides are red. The second card, both sides are black. The third card, one is red, one is black. You mix the cards randomly, and you show one card. You put one card down, and it's red. It's red. Okay. What is the probability that the other side is also red? Now, most people will say the following. I could not possibly be looking at that card. I could not possibly be looking at that card, because how else, how would I see a red? So either they see this card or they see that card. So there are 2 cards, and they're going to say, well, if I see a red, then yeah, the other side is going to be red. If I'm seeing the red, the other side is not red. 1 out of 2. They would think that it's 50-50. Okay, so somebody will play this game and they'll say, look, it's 50-50. Let's just kill some time and play this game. And in the end, we'll probably break even. But it's not true. Okay, so when I write XY, X will be the color of the front, and Y would be the color of the back. So we either have black, black, we can have black, red, we can have red, black, or we can have red, red. Now, that's the sample size. And this is where people get confused and they say the answer they have. This is the sample. We clearly are not looking at the blue card. Okay, we are not looking at the blue card. There are 3 cards that we could be looking at. If we're looking at this one, that other side is not black. Sorry, is not red. If we are looking at this card, we're seeing this red, because I'm telling you, you're seeing red. The other side is not red. if we're looking at that card, whether this is the front or that's the front, the other side is red. 1 out of 3. But a lot of people will think it's a half. So how do we use our Bayes' theorem to prove this? I'm going to use Bayes' theorem, I'm going to use real mathematics to prove that it's a third of the times, a lot less than a half, a lot less than a half. Okay. So, we want to know what is the probability that we get red, that is, we get this card right here, given that the front card we saw is red. We could reverse this. So it being this. The probability that the front card is red, given that we have the red card. Now, here are the cards we could be getting. The probability of red, given that we have the red card. The probability of red, given that we have the black card. Probability of red given the red-black card. Of course, for each of these, we multiply by the probabilities. I ran out of room, but here I'm going to put the probability of red, the probability of red, black. Of course, over here I could have said BR, black, red. All right. We're given that we have the RR card. What's the chances that R is in front? 100%. What's the probability of picking that card? 1/3. There's 3 cards and they're identical looking. We're going to randomly pick one. Identical looking means they have the same shape. So 1/3, 1 out of 3 times, we'll pick the R. The probability of getting a red front, given we pick the RR card, 100%. The probability of picking the red card, 1/3. Plus, what's the probability of getting a red for the front, given that we pick the black card? Answer is 0. You pick the black card, there's 0 chance of getting the red in front, times the probability of getting black. It happens to be 1/3 as well. What's the probability of getting a red on top, given that you pick the RB card? The answer is 1/2. Half the time the black will be on the front, and other half the red will be in the front. Times the probability of picking the red-blue card, 1/3. Okay, so if you notice, I can factor 1/3 out from the top, can factor 1/3 out from the top, from the bottom. Each term has 1/3, I can factor it out, and the thirds actually cancel. So what you have is 1 on the top, on the bottom, you have 1 plus 0, which is 1, plus 1/2. 1 plus 1/2 is 1 1/2, 3/2. That's 2/3. Multiply 1 by this flipped over. 1 times 2/3 is 2/3. So 2/3 of the time, the other card will also be red. So I guess if you want, so therefore, 1/3 of the time, the other card the other side will be black. So I guess we should have done, what is the probability that the other side is black? And it's only 1 out of 3, not a half. So the person says, I'll bet you even money that when I turn over this card, it'll be black. And you're going to say, well, yeah, that's pretty fair. It's even. It's either black or red. Okay. You either have one of those two cards, and either if it's this card, the other side is red. If it's that card, the other side is black. This 50-50. It's an even bet. I wouldn't take that bet if you paid me. You'd have to give me 2-to-1 odds, and then I'd play all night long. Okay, so we're going to revisit a very similar problem that we've done in the last section. You know that a family, which does not start with H, has 2 children. A family has 2 children. Okay? You randomly meet one of them. Let's just say for a moment the family has a boy and a girl. You're just as equally likely to meet the boy than the girl. Okay, none of this, well, girls stay home more than boys, so the chances you meet the boy is greater than the chance you meet the girl. Or girls go out more, they leave the house more often, than the boys. Okay, everything's equal. Okay, so you randomly meet one of them, a girl. What is the probability that both children are girls? What is the probability that both children are girls? Now, remember, you can do this problem, and we did do this problem using conditional probability, where we just looked at the reduced sample space. And since, well, you have 2 children, firstborn, secondborn, firstborn, secondborn, there are 2 options for each position, boy, girl, boy, girl. 2 times 2 is 4. Those are the 4. But you met a girl, so this one's out. Okay. In this one, you met a girl. The other one's not a girl. In this case, you met a girl. The other one's not a girl. In this case, no matter which girl you met, the other one is a girl. It's 1 out of 3. And we're going to prove this by Bayes' theorem, Bayes' formula. Okay, let's just get some notation down. G1 will be the firstborn is a girl. G2 is the secondborn is a girl. B1 is the firstborn is a boy. And B2, of course, will be the second child born is a boy. And G equals the want to see. G is the girl you met. The girl you met. Right. So, what is the probability that both children are girls, given that you met one? We want the probability of both children being girls, given that you met a girl. Okay. If you can do this problem directly, go for it. If you can't do it directly, you think Bayes' theorem. You say, you know what? I'm going to interchange these. The probability of girl given G1, G2, of course, times the probability of G1, G2. Now, G1, G2, what information is that giving you? It's giving you the sex of the firstborn and the secondborn. So in the bottom, I'm going to put all of that. Probability of seeing, given that you had boy 1, boy 2, times the probability of boy 1, boy 2, plus the probability of seeing a girl, given the first is a boy and the second one born is a girl, times the probability of B1, G2, still in the bottom, the probability of seeing a girl, given the first child is a boy, a girl, and so is the second, times the probability of that, plus the probability of seeing a girl, given the first child is a girl, but the second one's a boy, times the probability of G1, D2. Okay. Now, remember, the probability of B1, B2, B1, G2, G1, G2 is a quarter. You have two children. You can have boy, 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 girl, girl, boy, and girl, girl. And each one of these are equally likely. Okay, let me erase some of this, and we will compute this probability. And we will come up with a third. Or was it 2/3? No, 1/3. Okay, equals. What is the given that you have two girls, what's the probability that the one you saw is the girl? 100%. The probability of G1, G2 is a quarter, divided by the probability. Given that you have two boys, what's the probability your neighbor saw a girl? 0. Times the probability of boy, boy is a quarter. This probability. Plus, you have one boy and one girl. What's the probability that you saw a girl? Half. The probability of having a boy first and then the girl second? Quarter. Plus, you have girl, girl. You have two girls. This family has two girls. And you see one of their children. What's the probability it's a girl? 1. What else are you going to see? Probability of girl, girl is a quarter. Plus, one more. You have a girl and then a boy born in this family. So the chances you see a girl, half. The probability of having girl 1 and boy 2, a quarter. They all have a quarter. It's going to cancel out. The top is 1. The bottom is 0 plus a half, which is a half. Plus another half is 1. Plus another one is 2. The only thing is I was saying that family has 2 children. You randomly meet one of them. What is the probability that both children are girls? Let me just look at this one more time, please. That's 0, a half, 1. It's a half. It's a half. It's a half. My little diagram has a little flaw in it that I did earlier where I got 1/3 or 2/3. It's a half. Bayes' theorem doesn't lie. Okay. Let us do one more problem. So, this last one that we did, it had 4 possible outcomes for the given that. I want to argue it only had 3, and that's not wrong. After all, one of those probabilities in the bottom was 0. That is, if you saw a girl, we know you didn't have boy, boy. Okay, so suppose you have 3 stores, and they are named Store A, Store B, Store C. 3 stores. And you have some employees in each of these stores. In Store 1, you have A, you have 50. In Store B, 75. And in Store C, you have 100. And some of these employees are females. I'm going to tell you the percentage. 50% of the workers in Store A are females. 60% in Store B are females. And 70% in Store C are females. There are 225 employees. I just added 50, 75, and 100. Now, some people, some workers, some employees, they resign. And the probability that you resign is the same for males and females. Okay, the chances that you resign. If you resign, you could have been equally male or female. They're equally likely to resign. Of course, if 50% of the workers are female, well, then the other 50% are male. So in that place, they're equally, if somebody resigned, they're equally likely to be man or woman. But if 60% are women, if 6 out of 10 are women, that meant if 10 people resign, you'll have 6 women and 4 men. That's what it means by equally likely. It doesn't mean if 10 people resign, 5 will be women and 5 will be men. No. The same proportion. In Store C, 7 out of 10 workers are female. So if 10 people resigned, it'll probably be 7 women, 3 men. Okay, the question is, what is the probability that if a female resigns, she resigned from store C. Given that a female, what is the probability that she worked Just give me one moment, please. Okay. Let's try this again, please. Given that a female what is the probability that she worked in store C? Okay, so what we're asking is, what's the probability that she worked in store C, given that she resigned and she is female? Okay, so we reverse these. Try to do it without reversing it. C. The second, the part that comes after the given that, is the store the person worked in. So I keep the front part the same in the bottom, but I change the store. She can be from store A. This female who resigned can be from store B. Or the female who resigned can be from store C. And for all of these four probabilities, conditional probabilities, multiply by P of the given. I multiply by P of the given. I multiply by P of the given. I multiply by P of C. And we just crank it through now. The probability that she resigned and is female, given that she's from store C. So we are in store C. The probability that the person who resigned is female is 70%. 70%. The probability that you work in store C is 1 out of 3. The probability that you're resigning female, given that you're from A, well, 50% are females. So 50% of the people who resign from store A are females. Okay, times the probability of being from store A is 1/3. Plus, being a resigning female, given that you came from B. Well, 60% of the workers in B are female. They're just as likely to resign as a male. So 60% of the times, if you're given that you're from B and you resigned, 60% of the times it will be a female. The probability of coming from store B is 1/3. Plus, the probability that if you're from store C that you are a resigning female is 70% times 1/3. The thirds all factor out, and cancel. I'm going to move every decimal 2 places to the right. This is 70. In this term, I move decimal 2 places. In this term, 2 places. In this term, 2 places. I get 70 divided by 50 plus 60 plus 70. In fact, I should have moved this 3 places. I'll get 7 over 18. 7 out of 18 times you would have come from store number C. The probability that you worked in store C, given that you resigned, is exactly that. Except I do have some problems here, major problems, which I'm going to try to fix. The probability that you came from a given store is not 30%, is not 1/3. It's not 1/3. Sorry about that. Okay, so let's do this again. These probabilities, the conditionals were always right. The probability that you're resigning female, given that you came from store C, is 70%. The probability you came from store C, it's 100 over 225. There's 100 workers in store C out of 225 workers in all. It's not 1/3. In the bottom, the probability that you're resigning female, given that you came from store A, is 50%. The probability you came from store A is 50 over 225. 50 over 225. Plus, given that you're in store B, the probability that you are a resigning female is 60%. The probability you came from store B is 75 out of 225. Plus, now this last one happens to be exactly what's on top. So I'll copy what's on top. 0.70 times 100 over 225. What I will say is, if I multiplied each term by 225, it would vanish. 0.70 times 100. Multiply by 100, move the decimal 2 places. It's 70. 0.50 is half. Half of 50, 25 plus. Ignore that 0. 6 times 75 is 450. But move the decimal over 1 place, because 0.6 is 1 in. And you get 45. And 70 times 100, just like we did on top, is 70. This is 70 plus another 70. In the bottoms, you have 2 70s. In the top, you have 1 times 70. Don't always multiply, because the 70s cancel, and you get a half. Half the time, if you are a resigning female, you came from store letter C. This completes the section on Bayes' formula. They're not as bad as you think they are.